Alrighty, hello everyone. We are back. So this is going to be the very first of the lecture videos for DE1. I am going to be using this kind of format for pretty much all of it. Um, it's a nice format, a nice black screen, and I can write on it with my tablet, and it just works really, really well. So I can do things like that. I know you're less impressed, but the nice thing is I can do all sorts of nice colors and make all sorts of cool stuff. I can draw freehand, and then at a push of a button, I can erase it all. So that's the format we're going to use. Let's get started. So I'm typically going to use yellow for my style, my color that I write with, because I think the yellow on the black looks really nice. So we are now in section 3.2. So 3.2, and this is nonlinear models. So this is also called logistic equation. And that's what we're going to be deriving today. Okay, so way back before the break, we started off with uh, exponential growth and decay in 3.1. So 3.1, we had exponential growth and decay. And I'm going to go ahead and sort of rederive things to kind of get us a nice baseline before we jump into 3.2, which is actually not a bad section at all. So what we did is we said that in this model, the 3.1 model, the rate of change of a variable is proportional to how much stuff is in the variable. And so when we looked at population, we said that the rate of change of population, it's proportional to the size of the population. And that makes sense. The more people you have, the faster your population is going to grow. Okay? So we set that up like that, and then we made an equation out of it. We said, well, we'll say that it's going to be dp dt is equal to some constant of proportionality k times p. And this k, the constant proportionality, that is where our rate was going to be. This is our growth rate in the case of populations. And the reason I'm sticking on populations today is because the logistic equation, we're going to be deriving it exclusively using population. So it's going to be growth based, and it's going to be using pop. So I'm just going to refer back to 3.1 in terms of population only, so we have a nice smooth transition into 3.2. So with this model right here, it makes sense that the rate of change is equal to the amount of population times some growth rate. Okay, and the way that we solve that is that we use separation of variables. So separation of variables, here we come. We need to solve for our p, and then we'll have a nice expression we can use. So here we go. Very first clear of the day. Well, if I hit the right button, it'll work. Okay, there we go. So we start off with dp dt is equal to k times p. Okay, and then we did separation of variables. I moved all the all the p stuff over to the dp side and all the other stuff to the dt side. So I basically multiply both sides by dt, and I get, I'll do one extra step. dp is equal to k times p dt. Then I move the p over, so I get 1 over p dp is equal to k dt. And now that I have all the p stuff with the dp and all the t stuff, or in this case just a constant, with the dt, I can now integrate both sides, like so. And if I do that, I'm going to wind up with the natural log of p is equal to kt plus c. And now I will apply the exponential. And when I do that, I'm going to wind up with the natural log of p and the exponential on the left, and kt plus c and the exponential on the right. Okay? Now I've got the exponential of the natural log, and so they are inverses, so they will cancel. And we'll be left with p is equal to, well, e to the kt times e to the c. So that's what I would get if I broke apart the kt and the c. When I multiply the same bases, I add the exponent. So now that we have that, we then said, well, I can say that e to the c is also a constant, since e is a constant itself, so I can get p is equal to c times e to the kt. And that was our function, but I will make one last addition because p, this is the population at time t. So the population at time t. So I'm going to rewrite it as p of t is equal to c times e to the kt. All right. Now, if I want to find c, I need an initial condition. And so the initial condition that we said was that at t equals 0, the population is equal to p naught. Okay? So I can now say p naught, that's my p of t at time 0, is equal to c times e to the k times 0. So this is going to be e to the 0, which is going to evaluate into a 1, which means that my c is just equal to p naught. Okay, and so now I can rewrite it as the final version, p of t is equal to p naught times e to the k t. And this is our final form that we derived, or exponential growth of a population. Make sure that p naught is nice and easy. Alrighty, so this is the one that we're going to kind of start with, but the main thing that we need to do is think carefully about this model right here. All right, so let me clear the screen and we will get back to that. Let's see here, clear that. Okay, so I'm going to rewrite at the very top what we just had. We had p of t is equal to p naught times e to the kt. And this model right here assumes that we have a growth rate that is constant. So k is a constant. Okay? No matter what the population is, the rate at which it's growing, the growth rate, is always the same. Now, that doesn't make sense in the real world because unbounded growth can't happen. Eventually, you wind up reaching the limit of the resources for the system, and you wind up having the population growth slow down. So we need a new model that will accurately reflect that as we approach the maximum population possible in a system, that the growth rate will slow down. Okay, so we are going to do that by getting the next sheet of paper, making this new model. Now, this is an interesting one. Okay, we're going to start off very similarly. The rate of change in the population is equal to, here we go, this is what your book loves to do, R times P, looks where R is going to now be our growth rate. I guess they use R because it's a rate. But we're going to make one addition, times 1 minus P divided by K. All right, here we go. R is now our growth rate. It is no longer going to be our K serving as the growth rate for our initial equation that we had way back when we started 3-1. Okay, so R is now the rate, the growth rate, and K is now what we're going to call the max population. Okay, so instead of K being the constant proportionality of the growth rate, R is now the growth rate, and K is the max population, or as your book likes to call it, what I've seen in several other places, this is called the carrying capacity. Okay, it is the capacity at which the system is capable of carrying. All right, so let's see if this model makes sense. All right, so we're going to look at two cases. The first case, we're going to look at where the population is much less than the max population. So assume we have a very, very, very large maximum population and a very small actual population. So if K is large and P is small, then P divided by K, it's approximately 0. It depends on what the values are, but you can imagine for a really large population, if you had one person, a really large max population, I should say, a person of one divided by that really large population of one divided by the max population of whatever, it's going to be a really small decimal, which we're going to say is approximately 0. So if that is the case, then we're going to wind up with dp over dt is equal to our rate times population times 1 minus 0. Well, this is just a 1, which means we get back the original unbounded differential equation that we started with, which makes sense. Because when the population is really small and the max population is really large, growth should behave as if there are no limits because the resources are not the limiting factor at that point. So that is very good to see that when the population is super small, it behaves like unbounded growth. Okay, now let me go to the next one. Let me clear this. In case 2, we're going to have a population that is approaching the max population. So P is almost the same as K. Okay, so if that's the case, P divided by K is approximately 1. Okay, so I get dp over dt is equal to R times P times 1 minus 1. Well, 1 minus 1 becomes 0, so the rate of change of the population is almost 0. And that makes perfect sense. When the population is exactly the same as the maximum population, you want the growth rate to be 0. So it looks like both of the cases hold up, and this expression, this dp over dt is equal to R times P of 1 minus P over K is actually a pretty good model to explain what's happening out in the real world. So this is going to be our differential equation that governs bounded growth. And in this case, once again, K is the max population. Okay? Alrighty. So, just like we did with the original very simple exponential function, we are now going to have to derive an expression for p using this differential equation. And this one is way more complicated to do separation of variables on and to solve out for p than the original one. So what we're about to do is a shout out to everyone who loves the derivations in the class. If you want to skip this, you won't offend me whatsoever. But we have a few minutes of solid derivation ahead of us to go from this to something that looks like p equals. So if you're ready, we will go ahead and start in on that. Okay, so here we go. We've got our dp dt is equal to r times p times 1 minus p over k. Okay? Now, we're going to do separation of variables again. So I'm going to move I'm going to call all of this the p stuff and move it over to the left, and then I'll have r dt on the right. So if I move this over, I'm going to wind up with, divide both sides by this piece right here. I'm going to wind up with 1 over p times 1 minus p over k to the negative first power dp is equal to r dt. Okay? So now I'm going to find a common denominator to make this a single fraction inside. So 1 over p times k over k minus p over k to the negative first dp is equal to r dt. Now I can combine that to 1 over p. We're going to have k minus p over k to the negative first dp is equal to r dt. Okay, now I'm going to flip this because it's to the negative first, so it's 1 over this. So if I want to divide that out and I get rid of the negative 1, it just becomes the inverse. So this is 1, or is that the reciprocal? Yeah, I think that's the reciprocal. 1 over p times k over k minus p dp is equal to r dt. Okay? So now that I've got it into this form right here, I can go ahead and take the integral of both sides. So integral of this side and the integral of this side. And if I do that, I'm going to go ahead and combine this into a single expression. So I'm going to wind up with, up here, I'll have the integral of k over p times k minus p dp is equal to the integral of r dt. Now, this looks like a terrible integral, but we are going to perform a really elegant trick. So what we're going to do is we're going to say, well, this is the same as the integral of k minus p plus p over p k minus p dp is equal to integral of r dt. Alrighty? So I just basically added a 0 to the k. I have a minus p and a plus p right there together. Now I'm going to break this apart into two pieces. So this is going to become the integral of, I'm going to have k minus p over p times k minus p, and then plus p over p k minus p dp is equal to the integral of r dt. Isn't that nice? It's one of my favorite tricks I've ever seen. So now all I have to do is simplify that. It's going to become a 1 on top there. Simplify this, and becomes a 1 on top there. And so I wind up with the integral of 1 over p plus 1 over k minus p dp is equal to the integral of r dt. Okay, so let me clear the screen and we'll move to the next piece for that. I'll rewrite what we had at the top. We have the integral of 1 over p plus 1 over k minus p dp is equal to the integral of r dt. And at this point, I can now take this integral. I can do this one. So this becomes the natural log of p, and then I'll have minus, let's see, why would I do that? That's right, because the integral of 1 over k minus p is minus the natural log of k minus p. I was wondering why I had that in my notes, but that's exactly right, since it's a negative p right here. And so the du up on top would be a negative 1. So that's why I had that negative right here. Okay, so natural log of p minus natural log of k minus p is equal to, over here we're going to get our very familiar rt plus c. Okay, the next thing I'm going to do is multiply every single term by a negative sign. And if I do that, then this term here will become positive and this will become negative. So it will allow me to swap the order. So I'll have the natural log of k minus p minus the natural log of p equals negative rt minus c. Next step is I have a difference of logs here, so I can combine that into a single log. So this becomes the natural log of k minus p over p equals negative rt minus c. And at this point, I will apply the exponential. So I get e natural log k minus p over p is equal to e negative rt minus c. Now, these are their inverses, so we get k minus p over p is equal to e to the negative rt times e to the negative c. Okay, swing up here. Now, I can rewrite this e to the negative c as, oh, I don't know, maybe a b. Why not? So I'm going to have k minus p over p is equal to b times e to the negative rt. And why did they choose a b to represent the constant e to the negative c? Honestly, I think it's just because it spells Bert. That's the only reason I can come up with. It's the only time I've ever seen them change that into a different letter like that. But Bert looks pretty cool, so we'll just go with that explanation. Don't quote me on that, please. I could be totally wrong. So next thing I'm going to do is I'm going to split this into two pieces. So I'll have k over p minus p over p is equal to Bert. And since P over P, well, that's just a 1, right? I'm now going to move the 1 to the other side. So K over P is equal to 1 plus Bert. Make sure I put that other dot there, to the negative RT. Okay. Now I'm going to take both sides, and invert them. So I'll wind up with P over K is equal to 1 over 1 plus B times e to the negative RT. And then I will multiply both sides by K to get the final answer. P is equal to K over 1 plus B times e to the negative RT. And this is going to be our new expression that we can use. Wasn't that fun? That's actually one of my favorite derivations, so I hope you enjoyed that. We have a few more things to say about it though, so we're not quite done yet. Let me clear the screen. We'll start with that equation again. So let's see, here we go. Okay, so rewriting up at the top, I'm going to have P of T is equal to K over 1 plus Bert B times e to the negative RT. And if I think back to my unbounded model, I had P of T is equal to P naught times e to the kt, right? And one thing to note is that for this one, this r right here is the same as this k because they decided to change the variables. And the k over here is not this k is the maximum population. Okay, so with that in mind, if you look at this carefully, you've got e to the negative RT here, 1 over e to the negative RT, and then here you've got e to the KT. This piece right here is very similar to this piece. And so what we're going to do now is try to figure out an expression for B using this kind of symmetry, if you will. So it's not exactly mathematically correct, but what we're going to do is say, since these two terms are pretty much the same, then P naught is pretty much the same as this K over 1 plus B. So we're going to say P naught is equal to K over 1 plus B. And by doing that, it's going to let us solve for our B so that we can then use it in this expression. So we're going to have, first thing that we'll do is we're going to cross multiply and get P naught plus P naught B is equal to K. And then we're going to subtract P naught from both sides and get P naught B is equal to K minus P naught. And then divide both sides of P naught to get B is equal to K minus P naught over P naught. Okay? So this is going to give us an expression for our B. I don't draw a line straight through it. For our B, and that's all that we really need. We use the initial condition to solve for R, and we'll be good to go. So in every case, what we're going to do is step 1, solve for B, and all we need for that is the maximum population and the initial starting population, which we will always have when we start off. And the second thing is that we are going to solve for R. So we need to find this R. If we have this B and this R, we can then solve for any population at any given time. Okay? So let's do that with an example problem. Let me clear the screen. Okay, so for the first example that we're going to work, it unfortunately is hitting a little close to home right now. I would love to be able to change this, but I can't think of how to change it off the top of my head without thinking carefully about what kind of real-world system would emulate this. So we're going to go ahead with the problem, and the problem happens to be, talking about flu on the campus. So if we have flu on a campus, I know it's way too close to home, but this is for academics. We're just going to say that it is just normal old flu. Flu is on a campus, and the campus has 1,000 students. Okay? And what we want to know is if 50 students have the flu on day 4, how many will have the flu on day 6? Okay? So we're going to assume that the flu starts with a single student. So our P naught is going to equal 1. And you'll always be given the P naught in the problem. Our K is equal to 1,000. That's the maximum population since it's limited to the number of students. And we have at T equals 4, P of T equals 50. Okay? So first step is to find our B. So B is going to equal K minus P naught divided by P naught. So B is going to equal 1,000 minus 1 over 1, which is going to be 999. Alrighty, so we have our B. Now we need to use the initial condition to find our R. So just as a reminder, our model is P of T is equal to K over 1 plus BERT, B times E to the negative RT. Okay, so we're going to have 50 is equal to 1,000 over 1 plus, we're going to have 999 for B times E to the negative R times, what is our T? Well, T is 4, that initial condition. Okay, so I'm going to cross multiply, and when I do that, I'm going to get 50 times 1 plus 999 times E to the negative 4R equals 1,000. Then I'm going to divide both sides by 50 to get 1 plus 999 times E to the negative 4R is equal to 20. Subtract 1 from both sides. I'm going to get 999 times E to the negative 4R is equal to 19. And then I'm going to wind up with E to the negative 4R is equal to 19 over 999. And that one is a decimal that is approximately 0.01902. So I can now take the natural log of both sides, and I'll wind up with the natural log of E to the negative 4R is equal to the natural log of 0.01902. I had to go to the next page for this, so let's start right there. Here we go. I can actually hit that right. There we go. So let me rewrite that. We're going to have e to the negative 4r is equal to 0.01902. We took the natural log and we wound up with the natural log of e to the negative 4r is equal to the natural log of 0.01902. Alright, here we go. These are going to cancel. I'm going to be left with negative 4r is equal to the natural log of this. And I don't have that value because I kept it as this for some reason. And then I solve for r by just doing r is equal to the natural log of 0.01902 divided by negative 4. And this is going to be a negative value anyway, so that's a good sign. Our r winds up equaling 0.9906. Okay, so now that I have my r, I can use that in my original equation. So one more time, P of t is equal to k over 1 plus Bert b times e to the negative rt. Okay, so now I can say, what is my population going to be at t equals 6? Well, that means p is equal to, I'll have 1,000 over 1 plus b is 999 times e to the negative, well, I've got 0.9906 for my r, and then my t is going to be 6. And I can just put all that into a calculator, and I'll wind up with the population at t equals 6 equal to approximately, change that to approximate, ooh, that's a weird approximate, 276 students. So if there were 50 on day 4, day 6, you'd see about 276. And that's it. That's how you work every single one of these. There are no exceptions. Just like with exponential growth and decay, these are very simple methods. There's just not a lot to them. The fun part is in the derivation, I think. But they're extremely powerful. We'll work one more example, and then we will probably call it. So let's do one more. Clear the screen. So for our next example, we're going to have 40 elk are released onto a preserve onto a preserve that can sustain 4,000. I'll say support 4,000 elk. Okay. After 5 years, the elk population is 104. Population is 104. How many will there be after 15 years? How long until there are 2,000 elk? Alright, so this is a two-parter. So first of all, let's take down all of our information. We've got P naught is going to equal 40. That's how many elk we have to start with. We have our K, which is our max pop. That's going to be 4,000. Anything else? Oh yes, we're given that after 5 years the population is 104. So you're going to have at t equal 5, p of t is going to equal 104. And I think that's about all the information that we need. We can just look at each part as we get to it for the question. So first thing we need to do is figure out what b is. So b is going to equal, oh, my ink flow just went out. B is equal to, we're going to have K minus P naught divided by P naught. So this is going to be 4,000 minus 40 divided by 40. And just looking at it, it's going to be 100 minus 1, right? So this is 99. Okay, so now that we have our B is equal to 99, we can solve for K. Solve for our R, not K. So let's see, we're going to have P of T. You know what, I'll go to the next page for this one. Let me go ahead and clear this and start from scratch. Clear that, and we're going to have P of T is equal to K over 1 plus Bert, like so. Alrighty. So for our initial condition, we're going to have our POT value is going to be 104. And then we're going to have that's equal to K, which is our max pop of 4,000, divided by 1 plus our B, which is 99, times e to the negative. We're going to have, for our R, we're trying to find, so we don't know that, but we do know that the time that we had 104 at was after exactly 5 years, so just like that. So now we can solve for R. We're going to do the same process, going to cross multiply and do all of that, so I'll have 104 times 1 plus 99 e to the negative 5r is equal to 4,000. I'm going to divide both sides by 104. I'm going to wind up with 1 plus 99 times e to the negative 5r is equal to, I'm just going to go 3 decimals, 38.462. Okay, now I'm going to subtract 1. 99 times e to the negative 5r is equal to 37.462. E to the negative 5r is equal to, when I divide that off, I'm going to wind up with 0.378. And so now I can take the natural log of both sides. And when I do that, I'm going to wind up with negative 5r is equal to the natural log of 0.378. R is equal to the natural log of 0.378 divided by negative 5. And that R value turns out to be 0.195. Okay, so when we clear the screen, we're going to do part 1 with that value. So clearing it, we've got our P of T is equal to K over 1 plus Bert, like so. Okay, so we want to know what the population is. We want to have, so P, don't know what it is equal to, and we're looking for at 15 years, so 4,000 over 1 plus 99 times e to the negative 0.195 times the time at that point, which is 15. Okay, that's my R and my T. When I plug that in, I wind up with the population after 15 years. It's going to be exactly about 630. Exactly about what that was a good way to put that. It is approximately 630. Alrighty, now we're going to look for how long it would take for the population to hit 2,000. So for that one, we know what the P of T is. P of T is 2,000, and we can fill in the rest of the pieces. We have our K, we have our 1 plus our B, which is 99, times e to the negative 0.195 times an unknown t. And so now we just need to solve for this t. I'm going to cross multiply, and when I do that, I'm going to get 2,000 times 1 plus 99 times e to the negative 0.195, which that point's there, t is equal to 4,000. Divide out, I'm going to wind up with 1 plus 99 times e to the negative 0.195 t is equal to 2. Subtract 1, 99 times e to the negative 0.195 t is equal to 1. E to the negative 0.195 t is equal to, divide that out, I get 0.0101, and then take the natural log of both sides, and I'm going to wind up with negative 0.195 t is equal to the natural log of 0.0101. T is equal to the natural log of 0.0101 divided by negative 0.195. Okay, turns out that t is approximately 23.56 years. And that's it. That is exactly how you work it. You can either solve for population or time once you have your B and your R. So that's it. That's how every single problem is handled. Alrighty. So I'm going to give you some homework to knock out. So let's see. I want to go with, let me clear the screen. Clear the screen. I know I can do that. Oh, I said I can do that. My goodness, the screen is not wanting to clear. Hello, screen. There we go. All right. Okay, so homework is going to be the following. This is from section 3.2, number 2, and the following problem. Okay, I made this one up. So we start off, we're going to have 100 bacteria in a small petri dish that can sustain I want to say 10 million bacteria. Okay, so what I'd like to find out is how long until there are, here we go, A, 5 million, B, 9,500,000, and C, 9,999,999 bacteria. So if you can find those 3 times for me, that would be awesome. But pay really close attention to what starts happening when you start getting close to the population, the max pop. You already know that it should slow down dramatically, but you have to be really careful with decimals once you start getting values like this. So what I would suggest is that if you have any trouble calculating this, I know this sounds absolutely insane, but use Excel to do the math. Excel has extremely large precision. I don't know how large it is, but I can tell you I use Excel for all of my very large or small population growth models. It handles it like a champ. So if you run into any problems with your calculator for these, switch over to Excel and try it there. I think you'll have much better results. And that is pretty much it. I will work these problems as well as the previous problems that we had before the break when we get back. So that's it. Y'all have a wonderful, I guess, couple of days, and I will see you later. All right, bye-bye.